I'd like to introduce our speaker today, Professor Oleg Kargaltsev. He's currently faculty at George Washington University. Oleg did his undergraduate studies at Moscow Institute of Physics and Technology. His PhD was from Penn State, working with George Pavlov on X-ray and optical emission from neutron stars and pulsar wind nebulae. And he was subsequently a research scholar at Penn State, and then an associate scientist at the University of Florida, and he's currently at the George Washington University. Oleg's research includes a wide range of galactic astrophysics topics. It's funded by a large number of NSF NASA grants in the past, and for studies of multi-wavelength identification of galactic high-energy sources, pulsar wind nebulae, extended sources with Chandra, high-mass gamma-ray binaries, and many other topics. He's also an associate scientist on Veritas, and we have collaborated on galactic studies with Veritas in the past and hope to continue in the future. He's an excellent teacher. He has mentored several PhD students, undergraduates, and also high school students. So let us welcome Oleg for today's talk. And Oleg, you should tell us if you prefer questions during your talk or after, as you wish. But please get started.
Thank you very much, Reshmi, for the very nice introduction. I'm delighted to be part of this series of talks, which I find very interesting. Unfortunately, wasn't really able to attend the talks when they're live, but watched some of them on YouTube. So as for the questions, yeah, I am actually generally very open to questions during the talk. The only issue with Zoom is that I'm not always being able to see like raised hands and so on. So maybe we can, if you have a burning question, just interrupt me vocally. I mean, because I cannot maybe see your hand raised, and ask it by all means. But otherwise, probably best to ask most questions at the end, just as a matter of efficiency, and because I have plenty of things to show. So I hope it's okay with everyone. If so, let me start. So yeah, the topic that I have is extremely broad. It's about X-ray and optical emission from neutron stars and pulsar wind nebulae. But I will have to still touch upon other bands of electromagnetic spectrum like radio and GeV, just because they all intertwine together. So I'm sorry, it will be a little bit of a whirlwind tour, but I'll try to keep emphasis on optical X-ray and maybe even more emphasis on results from Chandra and Hubble somewhat space telescope. So I tried to arrange it all in some kind of meaningful structure, but I quickly realized that I have to cut some corners anyway, and so I will follow my preferences in many places rather than providing really entirely complete picture. I have these three parts in my talk, and the part one is basically just to review emission from neutron stars with a focus on X-rays and optical. Then I will talk about pulsar wind nebulae, primarily in X-rays, maybe show a couple other images. And then I'll try to discuss what makes this pulsar wind nebulae be so interesting and why they look so different. And the part three is kind of connecting some of the topics from part one and part two. In an attempt to make a joint picture of how pulsar properties leave an imprint on pulsar wind nebula properties. So that's the plan. Let's see how it goes. Part one, I would like to, again, for the purposes of efficiency, basically skip some very introductory remarks that could be made, but they will take time. And so the only thing that I would like to say is that a neutron star is an extreme object which has extreme magnetic field. And because it's rotating, in general, we expect that there's going to be charges in the magnetosphere. These charges can be pulled from neutron star surface, but then if the configuration is right, these charges can go through, initiate a pair cascade, right? And so they can multiply. And the only other introductory thing here is that there is two regions generally that people talk about. One is inside the so-called light cylinder, where plasma in the closed magnetic field part of magnetosphere rotates with a neutron star, and then the sort of wind zone outside the light cylinder. And so this light cylinder is basically obviously not on the scale with the size of neutron star is shown here, and I'm going to mention it a couple times, so it's good to know what it is. This configuration that is shown here is basically an aligned rotator, because you can see dipolar magnetic field here, and the axis of dipole, they are aligned with rotation axis. And in reality, of course, we don't expect them to be all aligned rotators, or maybe actually none are perfectly aligned rotators. But it is this angle that I will be talking quite a bit about between magnetic dipole axis and rotation axis, which is 0 here. And possibly the other thing to briefly mention is this P, which stands for polar cap, and that's the angular size of the polar cap, where you have this magnetic field lines that actually open up, so they do not close by the time they reach a light cylinder, and therefore they likely remain open to very large distances. So there's two things one can talk about, or try to mix them when talking about emission from neutron stars. It's the observables that are generally pulse profiles, variability, which can be periodic or not necessarily periodic, on variability on larger time scale, not so that there can be actually just like flares and magnetars, for example, or some kind of secular changes, slower changes in pulse profile. Also spectra, obviously, that can span now from radio to TeV gamma rays. And the other aspect is the demographics, which, of course, is related to the observables, because that's how we assign these objects to different classes. And actually, there is quite a few types of subtypes of neutron stars by now. I'm not going to cover all of those. The main ones are the pulsars, or what we call rotation-powered pulsars. The magnetars, CCOs, compact central objects in supernova remnants, and then there's this complex name, which I will sometimes abbreviate, but these are radio quiet but thermally emitting, mostly thermally emitting isolated neutron stars. So I might just omit some of these letters in future. So it's conventional to put these objects on the so-called PP dot diagram, which must be in every talk related to pulsars. And the largest population of neutron stars that we know, not necessarily overall the largest. That can be just some observational biases there. But most of neutron stars that we see appear to be what's called rotation-powered pulsars, RPPs, right? That's, you can see in this region of PP dot diagram. They range in their ages, in the strength of magnetic fields, so they occupy a fairly large area here. Then there's a subset of neutron stars that are called magnetars. They live over here. They have very large magnetic fields, and they believed to be powered not by the loss of kinetic rotational energy, but rather by the magnetic field activity. They will have very strong magnetic fields. The region here, like at the intersection maybe of those two, is this radio quiet isolated neutron stars, and they may be descendants of magnetars, kind of like older magnetars. Then in this region, there are the strange somewhat objects that are the CCOs. And then finally, if you move here, there's a very old pulsars that are, as you can see, with very short periods. They're called millisecond pulsars, MSPs. These are very interesting objects. In particular, they have this interesting diversity in terms of the binaries and binary companions. and not all of them in binaries, but they must have been at some point in binaries. That's how they span up to very short periods. And those that are still in binaries with a very close, very small orbital separation with some low mass stars, they call spider systems, redbacks and black widows. And so I'm not going to talk about those, and I'm only accidentally maybe going to mention a couple millisecond pulsars at all, but I'm primarily going to be focusing probably on this part of PP dot diagram due to the lack of time. Now I'll leave it up to you to think about the relation between this movie and the rotation-powered pulsars. Yeah, and if you want, you can ask me questions about that later. So the other I found online is very nice, the sources here, representation, which is maybe a little bit, not a little bit out of date, but still pretty good, is trying to sort these objects in this Venn type diagram. And so, for example, there's this like, most of the pulsars are solitary, but there's a lot of binary ones as well. They are mostly millisecond pulsars. And then among the solitary pulsars, we know quite a few to be in supernova remnants. And for those, we have better handle on their ages. We know for sure they are pretty young. And those are the most energetic and likely to have pulsar ring nebulae. So let me talk just a little bit, really, with possibly one example only about rotation-powered pulsars. So in these objects, the source of energy is the rotational energy of the neutron star, which is basically transferred to particles by means of electromagnetic field. The emission from these objects is actually can be quite complex. It's not just non-thermal emission from those particles, which are accelerated and therefore can radiate synchrotron, curvature radiation, inverse Compton radiation. But there's also a thermal component that is seen in some of these objects that comes from surface or atmosphere of the neutron star. And that thermal component can be seen usually in soft X-rays or UV. Here is an example of one of the pulsars, which is what we would say maybe middle-aged or oldish pulsar B1055-52. This pulsar has a nice broadband spectrum that is measured from actually radio, which is not shown here, but shown as the optical part going into UV, where you see this rise and excess over a power law, which we interpret as the presence of thermal emission from the neutron star surface, which is also seen in the soft X-ray range here. Which is likely, spans range of temperatures, meaning that the surface is not just a single temperature. So we can see this in this thermal spectrum. Then there is a power law component that is nicely showing up in the fairly narrow range of XMM Newton. So we're kind of lucky that it actually does not stop, the sensitivity of the detectors does not stop at 2 kilo-electron-volt, but goes to 10. And so we can pick up this power law component. And then there's a Fermi, obviously, now in measurements that are in GeV gamma rays. Now, one can try to connect these things, and they don't really connect. You can fit a power law here, there, and like there. But I think there's more to be done here because this spectrum is phase integrated spectrum. And even though the emission in this pulsar seems like to be confined to a single peak, this peak is looking not very peaky, right? And so you might suspect that it is actually several peaks merging, and their spectra in principle can be different if these are particles radiating different parts of magnetosphere or maybe even outside the light cylinder. The spectra can be different. And so ideally, a phase resolved spectroscopy should be attempted in this wide range of wavelengths, which is quite challenging, as you can imagine. And an interesting thing that I can show, maybe likely could be just a coincidence. If you just join these points with those using this line, it lands fairly close to those points. But again, the slopes do not agree. However, if one decomposes this into different peaks with different spectra, maybe something interesting can be learned there. And you cannot do this with this pulsar because it's too faint in X-ray and like hard X-rays, and the optical is pretty faint too. They all faint in the optical. But there's some pulsars that are brighter. This is a younger pulsar, well-known, Vila pulsar. And for Vila pulsar, the pulse profiles have been measured, in a very detailed way, as you can see here. There's two peaks that are prominent in gamma rays, the peak 1 and peak 2 traditionally called. And so you can kind of trace them across these multi-wavelengths plots. You can see that one of those peaks, peak 2, survives up to very high TeV energies, but then this peak 1 is actually more stable at other energies if you look at these diagrams, and the peak 2 behaves somewhat more diversely as a function of energy. It gets broader, smaller here, and so we don't quite understand what it means, but here we can try to decompose emission into coming from two different phase ranges. For example, at least peak 1 and peak 2. I just don't have time to discuss some other interesting behavior here. For example, there is an interpulse emission, which is actually seen also across multiple wavelengths, but let me not talk about that. So if one tries to decompose, then you can see that this peak 2 in principle has a better agreement in terms of extrapolating GeV spectrum to lower energies. I'm not fitting here spectrum to all points shown here. The spectrum is really just fitted to very high quality Fermi data here in GeV and then just extrapolate it. Note there is an FUV point here. One can argue whether I should plot it here or should not, because the peak is shifting a little bit from its position, peak 2 in far UV, but it's not inconceivable that this radiation is still produced by those same particles because of the complex things involved when there is a motion of, let's say, particles tied to magnetic field lines, and the magnetic field lines are therefore having some, so to say, inertia, and they are being opening up, and there is some retardation effect there, which I'm not going to go into details. There's obviously a very interesting thing to note also, as this TeV emission detected up to very high energies, 20 TeV, but my talk is primarily focusing on X-rays and maybe a little bit of optical, so I'm not just going to talk about it because it's too much, but it's very interesting. Now one can try to put X-ray properties in combination with something, and in TeV we don't have many detections of non-thermal emission from the pulsars, it's just few. But in GeV, of course, we have plenty of measurements, and so one can try to do a little bit of a population, kind of like a study or overview in terms of plotting X-ray and GeV luminosities. They can be plotted versus spin-down parameters such as E dot, and you can see that there's a substantial fraction of that reservoir of energy, which is rotational like power lost by the pulsar, is used to produce GeV emission. This line is when these two quantities are equal. And if you're wondering why there are points above this line, that probably is because of the inaccurate distance measurements that distances needed to calculate luminosity. You can also see either from this figure or from the figure below over here that the luminosities of X-ray luminosities and GeV luminosities are quite different, with X-ray luminosities being, and they measured in like 1 to 10 keV. Here, that are actually substantially lower in that energy range. So they are just a small fraction of E dot, but occasionally they can be an appreciable fraction of E dot. That's about 10 to the minus 1 of E dot line. So there's a lot of variation for some pulsars.
Oleg, may I ask
yeah.
a question?
Yeah.
Thanks. So I'm not asking why you're comparing the X-ray and GV emission. That is okay in general, but just to mention that these are emission bands are from electrons from completely different energy bands. So there should not be, I mean, a priori good correlation between them. Because it's just our different energy bands, and we know that at least in the case of the crop, that below a few TV or maybe 100 GV below, there should be some break in the electron spectrum, so GV should be suppressed. So what is your intention? What basic idea to comparing these two distributions?
Oh, the idea is just to show where the most of the energy is already emitted, and to also show the spread of efficiencies that is surprisingly large, maybe for some range of E dot at least, like over here. And I absolutely agree, Felix, that one should not a priori expect some strong correlation here between GeV and X-ray, for example, emission, luminosity. It may or may not be, right? Because if there is no break and there is a single power law, and then you can, and the emission side is just the same for X-ray and GeV electrons, GeV emitting electrons, then there could be, but of course there doesn't have to be. And I think it's still kind of meaningful to show this.
No, that is true. I just want to say a priori you should not expect such a correlation.
I'm not saying, yeah, sure, it doesn't need to be that.
And because I'm asking this, do you have some, so what is more relevant for GV gamma rays, energy band for synchrotron? It is observable or not?
Sorry, what's observable?
So, I mean, X-rays correspond to TV gamma rays or high energies, so they are coming from the same electrons. For GV gamma rays, basically this should be somewhere probably in radio to millimeter bands, right? So that would be interesting to compare the GV distributions with the low frequency synchrotron emission.
Yeah, I think this picture might be more relevant for that. So this peak, for example, right, it kind of peak 2 persists from TV at almost the same phase throughout GV. It does show up in harder X-rays, though of a different shape. And it actually slightly shifts, but still present in the UV and optical bands. So in principle, there could be different sites or even different particle kinds that are responsible for the emission from the two peaks. For example, there could be positrons emitting in one region of magnetosphere and the electrons in the other. This is kind of speculative, and I honestly don't want to move into that direction. But what I think is promising for understanding what's going on is the phase resolved multi-wavelength fitting, which can only be done really for several pulsars. And it does need to take into account possible delays, travel time delays or retardation due to deformation of the magnetosphere as the pulsar rotates through the line of sight. So those effects must be taken into account when we try to interpret things. I have to move on, unfortunately, beyond this very interesting, I guess, yeah, surely topic.
Sorry.
But thank you. Yeah. The other type of neutron stars, very briefly, is this radio quiet isolated neutron stars, because I'm just trying to give an overview of the entire population here. And these are characterized by predominantly thermal spectra. At some point, we actually thought that might be just entirely thermal perfect black body for this object, quite famous 1856. But then with an extraordinary amount of data collected by XMM, 1.4 megaseconds, it turned out that there is some signature of non-thermal emission. Also, there is an interesting thing that is actually seen in the optical or near infrared. These objects, they actually, if you look at them in the let's say from infrared, near infrared to far UV, if you look at them, the spectrum, the extrapolation of thermal spectrum undershoots significantly their far UV or optical fluxes. And moreover, the slope of the spectrum at those lower frequencies does not look like Rayleigh jeans, perhaps with the exception of this object, which still has UV excess. So there's something interesting going on. And it's not currently clear whether it's all non-thermal emission or there's some atmospheric effects. But here you might interpret this part as an evidence of non-thermal emission and some kind of particles in the magnetosphere of these otherwise very thermal neutron stars. So Irazita should be able to find more of those, and there was a recent report of finding very good candidates there. The other obviously very important well-known type is the magnetars. So the magnetars, there's about 30 of them known. There's this very nice catalog at McGill. There is mostly they are detected in X-rays when they go into flare, right? But it's interesting that sometimes you can see them as sources that are near infrared or optical sources. And this is an example of one well-known source, just one example, for which we have probably the best measured low energy spectrum, because we even took the JWST observations recently, which show very flat in new FNU spectrum here. And then there's some older optical, previously measured optical points. They don't show X-ray data, but they kind of follow this black curve here, and how you fit the X-ray data, it actually depends. You can try to fit a soft power law here instead of a second, for example, black body component, or you can put a second black body, but this part does look pretty thermal. And then there is a tail, which I don't want to get into this, but let me just mention that one can try to interpret it as a due to resonant Compton upscattering of thermal photons, or as actually emission of some non-thermal distribution of particles. If you try to extrapolate this, assuming it's just a power law, it undershoots those points by a huge margin. So that therefore this component is actually there must be either strange break, not a cooling break in a sense, that's what's strange about it, or two separate emission sites or emission processes. We are still trying to understand the properties of this near-infrared emission. Would be good to try to measure pulsations with JWST to see that it's truly non-thermal. Because there are suggestions that there may be some contribution of so-called fallback disk here, but we don't see curvature here that is expected for the fallback disk. The other type is so-called central compact objects. Those are very young. They're very young because they are in very young supernova remnants. They're called central objects because they are in the centers of supernova remnants. That's the most famous one. And I'm just showing as an example of how they look like. They are virtually, the only emission you can see from them is virtually just X-rays, and those X-rays are thermal. You cannot, however, describe X-rays entirely by a black body, but you have to use either multi-temperature or atmosphere, multi-temperature black body or neutron star atmosphere, and there are varieties of those. I don't have time to go into those details. This object is particularly interesting because 300-year-old, and it seems to show some changes in temperature over well, 20 years or more. It has been monitored with Chandra. Now, these are very hot, obviously, but because they're very young. But the interesting question is, let's say, how does the temperature of neutron star evolves with age? So very hot means millions, right, of degrees. It's over here somewhere, very young neutron stars. But then we do detect some very old neutron stars in, let's say, far UV. It's very difficult. We found that extremely old neutron stars, such as millisecond pulsars, the most famous is perhaps this one, 0437, seems to have temperature of about 100,000 Kelvin, which is much more than you would expect for passive cooling. And therefore, all kinds of interesting processes must be considered to keep it warm, including dark matter accretion. I'm not shown here, but I just don't have time to go into those processes. It seems that the old millisecond pulsars can stay warm, and also the old normal, like ordinary pulsars that are not spun up due to accretion can also stay warm at large ages. So this is just some concluding remarks. I basically said all of this kind of. It's interesting to try to do this multi-wavelengths phase resolved keyword spectroscopy and multi-wavelengths too. One has to try to understand the shifts in the peaks at different frequencies, and that probably informs us about the sites of emission, which can be different for different parts of the light curve. I didn't have time to go into this, but it does seem indeed from recent results that at least some substantial amount of emission in like Vela pulsar has to come from vicinity or outside the light cylinder. The magnetars, the evidence of non-thermal emission, I think, is interesting, kind of building up now with this JWST measurements, possibly. And then I just, sorry, there's interesting topics here, but I don't have time to go into that. If I may, I'll move up to my second topic, but you can ask me questions about all these parts together at the end. Now, the second topic is mostly pulsar wind nebulae. This pulsar wind nebulae, again, I'm just going to skip through most of some very introductory remarks, just mention several basic things. So here is a picture, which is again not up on a scale, but that's kind of like light cylinder. And then there is this pulsar wind, which is initially extremely relativistic. The velocity is about speed of light, actually very close to it, the bulk velocity, the bulk motion of this wind. It has to slow down somehow because there is a pressure in the outside medium, so it has to slow down. And we believe that there is a termination shock that develops here, which can be also viewed as a reverse shock standing in this wind. And the usual words that are said is that the particle pitch angle distribution is somehow isotropized here, and the energy of the bulk motion and of the magnetic field that is believed to be higher here is converted into the energy of the particles. Where does this conversion happen and through what process? Because it basically means particle acceleration is yet somewhat of subject of debate. But the energy gain is substantial between what we think Lorentz factors of particles over here, just outside of the light cylinder or in vicinity of it, and outside of the termination shock. The change in Lorentz factor is probably something like a factor of 1,000. well, it varies maybe from pulsar to pulsar, but there is a significant energy gain by particles. So somehow this energy is transferred. Now it's popular to talk about, let's say, magnetic field reconnection, even with respect to pulsed emission from pulsars, but obviously also with respect to transferring energy to pulsar wind particles. Some observables here are the synchrotron photon energies. And when I say here, I'm now focusing on this region, which is called synchrotron nebula, beyond its termination shock. We see X-ray emission. I'll show you multiple pictures very soon, so you can relate, these X-ray photons to basic parameters that are in the synchrotron theory, like magnetic field and Lorentz factor. And if you take a 2 keV synchrotron photon, then you can, write this down as this equation. But of course, it's just somewhat arbitrary energy, because we see higher energy emission from pulsar wind nebulae and lower energy, right? Then you can also estimate what would be the energy of inverse Compton upscattered photon in a pulsar wind nebula, which is produced by those same electrons that produce 2 keV synchrotron photon, right? And therefore, instead of using gamma, I can use the synchrotron photon energy here, just a simple substitution. And you will see that these electrons, they are producing 2 keV synchrotron photons and 10 TeV inverse Compton photons. Now we can see sizes of these nebulae, we can kind of measure them, and one can scale this by balancing, can get an estimate of the characteristic size, length scale of this termination shock by balancing ambient pressure and pulsar wind pressure. Of course, the ambient pressure can vary, the dot can vary, but if you scale it, the size to these values is the right fraction of a parsec, which of course which is in agreement with what is seen for some pulsar wind nebulae, and of course there should be a range here in reality. Now the other thing to note is the cooling time for particles emitting at 1 TeV is actually longer than the cooling time for particles emitting synchrotron photons that we see at 1 kiloelectron-volt, and therefore the consequence of this that we can see kind of like the older population of the electrons in TeV gamma rays rather than in X-rays. And then there's, of course, this usual game of playing this efficiency, which I did show you for pulsars, these lines that I plotted in those population plots. It's this efficiency of conversion of E dot into, let's say, X-ray luminosity, but in principle, you can look across multiple bands, or even do a bolometric one by integrating. Let me not dwell on this picture just to save some time, but we are in this talk are going to focus on this kind of like maybe inner region of the pulsar wind nebula, because that's where probably X-rays come from, because of the shorter cooling time. But of course, there's a very interesting topic of these large TeV sources and TeV halos, and there may be different processes of transport, like more of an advection here and more of a diffusion and larger scales that are involved, but I'm not going to go that far in the distance. So I'm just going to mention that there's a lot we gained from the having Chandra, XMM Newton, and more recently IXP, because we can separate pulsar from pulsar wind nebula on a very small angular scales. That's that advantage of Chandra, right? Then the Chandra can resolve the structures. That's the key that's where I'm going to focus now on pulsar wind nebulae, the structure. And also actually allows for spatially resolved spectroscopy with ACES detector on Chandra, because you not only resolve, you can measure spatially resolved spectra. So you can kind of try to measure the injection spectrum close to the termination shock, injection into pulsar wind nebula spectrum. So you can also resolve faint sources or faint extended sources. That's not necessarily easy thing to do, because if you have a high detector background, for example, with XMM Newton, that's very challenging. With Chandra is actually doable, and those are probably most numerous pulsar wind nebulae around older pulsars. The localizations are also extremely important, subarc seconds, because then you can classify the source and actually understand that it is a neutron star. The measuring spectra of objects in complex environments like supernova remnants also would not be possible with high resolution. So that was mostly Chandra, but then this ability of getting pulse profiles and then maybe doing phase-resolved multi-wavelength spectroscopy, you have to have the pulse profiles measured in X-rays. That's where XMM comes from. And then the XP is allowing us to understand the structure of magnetic field and the degree of its regularity in the pulsar nebulae. These are kind of just nice movies that actually show that we are looking at quite dynamical structures. And the dynamics is actually different because here the most dynamical kind of structure is this inner ring, and then here it's maybe the most dynamical structure, not those arcs, which are maybe equivalent of this inner ring of a termination shock, what we think is where the location of the termination shock. Now here is the jet is the most dynamical structure, and there's other examples that I can show. Just one of them is this recent observations of 3C58 over 20 years time span, which shows that this feature does actually move. You can see that the images are registered by looking at this source that is not moving. And so likely it's the jet, which actually might actually exhibit somewhat of a similar corkscrew structure to those. But then there's more complex structures like loops here, which probably are not related to this jet, but I don't have time to talk about those. The measurements of magnetic field, that's what can shed light on some of those interesting structures. Unfortunately, the objects need to be very bright to measure magnetic field, though it is still quite interesting thing to do, and it has been actually done with IXP. These measurements are done for Crab, Vela, and MSH 1552. The common thing is the high degree of the high polarization fraction and the regularity of the magnetic field, which seems to exhibit a toroidal structure, right? This is somewhat maybe surprising, not entirely expected to see such a regular magnetic field, because you can expect that there's a lot of turbulence is happening, right? And the picture might look something like this. Also, even here in this nice 3D simulations, you can see that there is this regular component of magnetic field. Now, let me take a broader view of this population because it's quite diverse, and you can expect it to be diverse for maybe two reasons. One is the properties of the ambient medium, and one way to characterize it is this, let's say, the Mach number. So it's so it's not only ambient medium. So it does come into play what kind of pressure and density you have in the ambient medium, but it's also pressure due to motion of the pulsar. And so one important parameter is a Mach number, and here is the sound speed in the medium, and that's the velocity of the pulsar. So, and the other parameter that one has to keep in mind is obviously varying properties of pulsars, but not only E dot. Now I'm just would like to draw your attention to these angles, which are parameterizing magnetosphere and our direction of our line of sight, zeta angle, with respect to the spin axis of the pulsar, right? And the alpha is this inclined dipole angle. So let's try to see how those come into play. In ideal situation, which doesn't realize where the wind is spherical, but it doesn't, it's not, you could expect to see something quasi-spherical for pulsars that moving very slow and something cometary for those that are moving very fast. We see neither of those morphologies. And if you add anisotropy, you'd say there should be maybe torus and jet here and some kind of structured tail. Well, the actual picture is indeed resembling torus and jet picture for these kind of slow-moving pulsars. But for fast-moving pulsars, there is an interesting complication, and the picture is quite different from the expected one. So let's first briefly look at the torus jet pulsar wind nebulae, kind of similar to Crab, but even here there's a lot of diversity. So sometimes you see this double arc structure and sometimes not. Here's again an example of the double arc structure. Some details here that I think are important is that if you look at the other nebulae, which do seem to have torus and jet, they can have very different strengths with respect to each other, right? This is a very faint torus. It's there, but very faint. The jet is very prominent, just like here. And the interesting thing is, again, these helical structures of the jets, they seem to be appearing everywhere. Now, if you have very high quality images, and these are, with lots of photons, you can do spatially resolved spectroscopy. And you can try to measure this, the index, spectral index of synchrotron radiation as close as possible to the pulsar, right? And you can reasonably maybe hope, at least for some of these nebulae, that there's not a lot of cooling happening yet. And so you're looking at the injection SED, and basically this photon index tells you, because it's connected to the electron SED in this simple synchrotron theory for uncooled spectrum this way, you can think that you may be measuring this SED spectra, right? SED slopes, sorry. If you convert from photon index to the SED, electron SED slopes, you can see that there's some harder spectra than you would expect for like very commonly discussed slope compared to this 2 for Fermi type acceleration. One can now look at the larger sample for faint pulsar wind nebulae, because you can think that you only see the brightest part of the nebula if it's faint near the pulsar, and it's maybe still uncooled, and you can get a broader distribution which sort of resembles it, but then you pick up more of this harder spectra if you look at fainter pulsar wind nebulae. So yeah, that's still preliminary work in progress. You can also see a lot of scatter in the efficiencies of pulsar wind nebulae, which is maybe somewhat unexpected, right? Because for pulsar, you can expect a high degree of beaming. For the pulsar wind outside of the termination shock. It's not moving already with bulk relativistic Lorentz factor that is large. It may be just slightly above 1. The velocities of 0.5 c has been measured, but it's 0.5 c. So this scatter has to be explained somehow. There's an interesting correlation, though, between the non-thermal luminosity of pulsar in 1 to 10 keV and pulsar wind nebula, but I don't have time to get into a lot of details. And there's some kind of agreement between the pulsar, the slopes of the spectra, but that's like a separate discussion. Now, very briefly about the supersonic pulsar wind nebulae. So we would expect something like this. Even if you have torus jet, everything gets crushed, compressed, and maybe you can have this structured tail, right? I'm just not going to go through the estimates. The purpose of this slide is to say that in irregular ASM, the sound speed is low, and so pretty much every pulsar should be moving supersonically once it gets out of its own supernova remnant. And these are numerical simulations which kind of can confirm the expectations. So these are actual observations, and you can see that the tails sometimes look like a bow, sometimes looks like a tail, sometimes look like a mushroom with a tail, and sometimes looks like don't know what. And most recently, we started seeing in very deep observations with Chandra structures that can be at a very large angle with respect to the velocity vector. So this is a tail, and this is what we call misaligned outflow, sometimes called kinetic jet. This is totally not fitting in the hydrodynamical picture, right? It's interesting that we probably did not find many pulsar wind nebulae because we were looking at this pulsar wind nebula, but then you look at the objects nearby, and then very small, like few arcsecond scale, you notice some extended object, which actually turned out to be later Fermi pulsar. So these are the little faint pulsar wind nebulae are yet to be found. Now let me talk about these misaligned outflows a little bit. I think this is quite interesting to understand. So that is where MHD descriptions likely breaking down and particles are escaping in the interstellar magnetic field. Whether they modify this magnetic field or not, that I think is a hot subject now, subject of debate. But these can travel for very large distances and apparently in a very collimated structure, right? That appears to be here, but then it expands rapidly. And so let me ask you to guess where you would expect TV emission to be coming from in this case. I'm just leave that question out there. These misaligned outflows have interesting structure, which is like apparently filamentary, and they are probably formed due to escape of very energetic particles from the apex of the bow shock, which is compressed, and this is related to what's called this magnetic draping idea. Right, and you can kind of see them even escaping if you actually zoom in. There's two little microjets here, and these microjets, they bend like these magnetic field lines in this simulation, forming these two outflows. The outflows are notably asymmetric. You can also see these outflows at harder X-rays. This is new star band up to 80 keV, and you can see this emission from here, just like you saw it in Chandra. So there's a very slow cooling and a rapid transport happening here, I think. These are very nice theoretical works, simulation by Maxim, of how this actually escape is happening, and by Barbara and Nicolo, which implies some interesting charge separation and possible instabilities developing. This is a plot borrowed from Roger Ramani, where there is this reconnection of external field, and this is the internal field, and they happen to go in opposite direction in some place. So that might be reconnection point and where these particles leak out. We are trying to study them more. These are multiple misaligned outflows. This motion vector is shown by the arrow, and that's the object I was mostly talking about before. I think it's a very interesting one. There might be misaligned outflows in radio, which would be somewhat unexpected because we are expecting the most energetic particles to escape from the apex of the bow shock. And so one has to think more about it. And we are trying to get 700 kilosecond observation with Chandra of the Lighthouse Nebula now. Don't have time to talk about the emission at other wavelengths. So the only interesting thing I say this development of seeing the bow shocks, not only in H alpha, but in far UV recently. And there's 3 pulsars that are now currently bow shocks I seen in far UV. The nature of that radiation is somewhat puzzling, of UV radiation or far UV radiation. And then there's varieties of this interesting pulsar wind nebula apparently in a binary system, gamma ray binary, where there's this ejections of plasmoids happening at velocities of 20% of speed of light. But that's I don't have time for. And there's an interesting object that is probably the only magnetar wind nebula that is like I'm very sure of. Is around one of the magnetars, which suggests that magnetars do produce copious amounts of particles, at least occasionally. And I'm not, again, going to talk about it. Now, very recent radio surveys, they suggest that there may be some counterparts to this TeV halos, right? There's some structure, you can see this in Meerkat, which seems to be like an arc pointing this way, and it kind of fits the TeV morphology, but we would like to have better resolution at TeV to study those. That's a summary of what I just said. So I'm not going to kind of read through this. It's the open questions that I sometimes mentioned, like nature of FUV emission, or like where this acceleration is really happening. There's something I didn't talk about, the neutron star kicks during supernova explosions. But these are related to measuring motion of pulsar motion morphologies of pulsar wind nebulae and velocity vectors. Let me just take another 5 minutes, sorry, and talk about the connection between the two topics I was focusing on. So these morphologies that we see in pulsar wind nebulae would be interesting to relate them to these very diverse light curves that we see in GeV gamma rays. The rotating vector model is kind of attempting to tie the morphologies of gamma ray light curves to these angles that I mentioned before, right? The alpha and zeta. And very briefly, the asymmetry between two jets and the degree of ellipticity of this ring associated with termination shock informs us about zeta. The strength, relative strength of equatorial and polar components is likely related to alpha angle. And this luminosity, overall luminosity of the nebula, I told you that the efficiencies of this nebula vary wildly. It's likely to be maybe correlated also with the angle alpha, because the size of the reconnection layer in the current sheet outside of the light cylinder, the area of reconnection, may be dependent on this angle. And so the slopes also, the spectral slopes, may actually show some correlation with this angle. So it would be very interesting to put together information from pulsar light curves and pulsar wind nebulae. Moreover, the simulations indicate that there is indeed dependence of pulsar wind nebula morphology on this angle alpha. This is more of orthogonal rotator, and this is more of an unaligned rotator. And Crab is mostly orthogonal rotator, strong toroidal component, well-separated peaks. The peaks get closer to each other as this viewing angle becomes smaller, right? And then this separation then can inform us about this angle, but also the ellipticity of this ring is telling us about this angle. So one can approach it from both ends. This is single peak light curve. So these are likely smaller viewing angles, and sometimes there may be also small alpha angles when actually you don't see much of a toroidal component, but you mostly see a polar outflow. These are extreme cases, I think, where you just like mostly seeing polar outflow, and these are likely small angles zeta, which you can measure from Doppler boosting that you observe here, or from the fact that this appears as a ring, not as an ellipse. Right, these are also the cases where you likely have small alpha and you don't have any gamma ray pulses. And that's what you expect from most of the magnetosphere models when you have small alpha and small zeta. Right, let me just say that these measurements are also possible for bow shock, like supersonically moving pulsars, because you can see some of that morphology in some cases, which you can attribute to jets bent backward and very faint torus. And so you can still get those angles, and you can still compare what you infer from PWN morphology to the light curves, even for these cases when there is a deformed pulsar wind nebula. So that's something interesting, I think, to do. And finally, one can use these misaligned outflows maybe to put some interesting constraints on the Lorentz factors of particles. So if they actually leak into interstellar magnetic field, then you can substitute into this synchrotron formula 5 microgauss, just typical value for the interstellar magnetic field. You see the X-rays, right? So 8 keV, let's say, X-rays. That means the Lorentz factors are pretty large, like this. And you see these large Lorentz factors, even for fairly low E dot pulsars, right? So the maximum Lorentz factor for this pulsar guitar is about 10 to the 8, but you still see emission at 8 kiloelectron volt, right? What does it mean? Why this maximum Lorentz factor exists? Because there is a potential drop across a polar cap, and that's probably most of the energy that is available there that the particle can gain. So how can this one exceed that one? I actually do not know the answer, but it may be that the magnetic field is actually amplified in those misaligned outflows by the beam of particles, of escaping particles, and then it can be higher here, reducing this value. One can also try to estimate magnetic field within the nebula from this condition of escape, the gyration radius larger than standoff radius of the bow shock. But I don't have time, maybe go into depth here. And so this is my last slide, the summary slide. So I think the promising area here is try to marry the information that we get from pulsar light curves and get from pulsar wind nebulae about the geometries and then try to compare maybe luminosities, X-ray luminosities of pulsar-V nebula for pulsars with similar alpha angles. And then the spread in the efficiencies may become smaller. And one can also try to see how the photon indices for pulsars with similar photon indices of pulsar-V nebulae of the injected SED depends on the alpha angle. Or one can also use this to discriminate, obviously, between different magnetosphere emission models, the information that comes from the pulsar-V nebula. Lastly, one can try to understand the origin of these actual jets that are along the pulsar spin axis, not the misaligned outflows, which sometimes called kinetic jets. And so this can be possibly done using the spatially resolved spectroscopy, which I didn't have time to show you the spectral maps, but they are interesting, and we are using them to try to measure uncooled injection index at determination shock. Thank you very much for your patience. Sorry to be a little over time. Thank you. Yeah, please ask questions.
Thank you, Oleg. That was really great. Very nice, comprehensive summary. Questions, if anyone?
Yes, Felix.
Yeah, sorry, I interrupted you. I think it was not a good idea because
That's all right.
confuse you. So my question was a bit related to these correlations, maybe out of this discussion, but it's quite interesting. So you know that there are now pulse TV gamma rays from Crab and Villa.
Yeah.
And most likely these guys are coming from inverse Compton. And if so, then target should be X-rays, most likely. So we should see correlation between TV and X-ray, pulse emission, I mean. And even gamma rays could be just slightly outside light cylinder, but still very close. So my question was how we could get from these correlations some answers about the radiation mechanism. I know it's a very old question. So if you search for correlation between GV and TV, ideas, if I understand, is that they should be the same mechanism, right? Like synchrotron or whatever inverse Compton. And that just question is the extrapolating electron spectrum to low energies to get X-rays and GV gamma rays. So what is your conclusion from this correlation? So what is the mechanism you are talking about? Gamma radiation mechanism and X-ray radiation mechanism. Do you think is the same process, the single process, responsible for X-rays and GV gamma rays?
Yeah, that's very interesting, right? So, well, the typical processes that I discussed, obviously, are the curvature emission for the GeV gamma rays. Sorry for scrolling so fast. I'm just trying to get to a relevant slide. The curvature emission for the GeV gamma rays and the synchrotron emission for the lower energy, right? Lower energy. Or alternatively, in principle, it could be synchrotron for both GeV and X-ray, let's say, radiation.
So the GV synchrotron still is allowed, right? Is under consideration or not?
Well, I'm not serious not doing the models, but I don't see why it would be out of the game if the radiation is happening like in the current sheet where the reconnection is going on. The magnetic field can be varying there, right? But in the very region where it's happening can be low, just outside of this current layer can be high. And so this picture that I have here for this peak 2, but only for peak 2 because it's different for the other one, is actually basically showing that you have maybe a single power law that is going all the way, right, from hard X-rays to GeV gamma rays. And I think this would be more consistent maybe with the synchrotron, right, than the curvature and synchrotron processes.
Yeah. Okay, just
But
this is
I'm not a theorist. Yeah.
comment is just, it is interestingly, that could be the third option. I mean, because TV, we are sure that is almost sure. Never say sure, but this is inverse Compton.
Mhm.
Then could be that GV also is inverse Compton. And so that was my, so is it, is all this correlation, could you make some?
I would expect to see difference then, because X-rays cannot, I don't think, can be inverse Compton, right?
Yes, I agree fully.
Expect to have a different, like a behavior, some kind of change in the shape of the spectrum if these are, let's say, these are inverse Compton and these are synchrotron.
No, I fully agree. So it means that GV cannot be inverse Compton, right? I mean,
I don't think so, but again, I'm not a theorist. Yeah.
Okay, so that was, I just wanted,
But
because
again,
TV
I'm
most likely is
discussing,
inverse
yeah,
Compton.
Felix, it's important to say that I'm discussing this, looking at this single picture for only one peak in the villa of the pulse, right? The other can be different peaks.
And was
Okay, so I think
easy.
Maxim?
Yes, Oleg, I have a question comment to almost last slide on your presentation,
Sure.
just before conclusions.
These are backup slides. Sorry, yeah. Is that this one maybe, yeah? No?
Yes, yes.
Mhm.
Here you assume a very low field in a filament.
Yeah, because it just substituted ISM field. Yeah.
But again, like if it will be the same, like a field as in ISM, normal one, you will see it more symmetrical stuff. And you should have something special to make visible such structures from one side, presumably. Because like escape from to left and right will be more or less the same. It's very difficult to make a strongly asymmetric flow.
Well, I again not, yeah, understand totally. Thank you, Maxim. Your question. Maybe there's one picture I can show, but also there is this paper by Barbara, I think, yeah, Olmi, a very recent one discussing the asymmetries.
I know it,
But then I'm very simple person, mostly an observer, really. And so for me, pictures, these pictures are maybe too complex. But this picture kind of suggests that, let's say, if you have something like a magnetic field that goes in two different ways here, and it goes in one direction, although it is curved due to this draping like this, and maybe here you wouldn't have a reconnection, while here you would have reconnection.
No.
And so it's kind of one-sidedness then. No?
Here it's a funny story, but if you have reconnection, you broke lines in both directions.
Okay.
So you will have escape as on the left as on the right, and it will be almost symmetrical. It for such high energies which you need for electrons, for leptons, to be honest, it will be not a problem to escape on both sides.
Mm-hmm.
And if you make like a field in the emission zone higher in this filament locally, this filament is high emission zone, high magnetic field zone. You easily explain emission, and second one, you easily relax power restrictions which you have in this case. So you solve two problems simultaneously.
Yeah. I did even mention the amplification of the magnetic field. That is it. On that last slide, there was a comment, and it is discussed in several, papers, that this may not be ISM field, because it can be modified by the streaming particles. But still, Maxim, I didn't quite maybe understand if the escape is symmetric on both sides. What's the explanation then in your your explanation for one-sidedness?
If you
Quantify
have
the field.
magnetic field
Yeah,
on the
but
right side locally, no, right side.
you mean it's locally stronger? It's not
Yes,
yes,
it's
but
only
locally.
here. You have the same magnetic field line, and it's varies magnetic field strength along this line.
Well,
And
so
You mean
interstellar
magnetic field
medium.
measured or modeled?
like in this case, it's modeled, but like how you can measure? Maybe it's
With gamma
exactly.
rays, obviously. Gamma rays don't depend on magnetic field. If you
Mhm.
can measure gamma rays, if there's no, if you see the same jet type structure in gamma rays, it means it comes not only or without magnetic field, just is distribution of electrons, because it's the product
Exactly.
of two factors, distribution of
Yes.
electrons and magnetic field. So how to separate them? I mean, okay, if your models gives you that jet structure for magnetic field, that is okay. But on the other hand, so only gamma rays. I mean, combining gamma rays, you can do that.
Exactly.
Yeah. So for instance,
It can be proof of this theory or this idea.
Here I would expect if most of the electrons really go in this way, not just magnetic field stronger, then the TeV emission here would be offset by, it's probably going to be mostly coming from here somewhere.
But here it could be quite difficult to see something in TV emission if it's amplification of magnetic field.
Right.
Because this signal will be very, very low.
Right. Yeah. But on the other hand, isn't it going to be a lot of kind of unlikely coincidence when you have multiple cases, right? And it just so happens that on one side there is a strong gradient in the magnetic field strength, and it's just stronger on one side of the pulsar and weaker on the other in all multiple cases.
But again, like if you have, if it's normal, if you have if it's like a normal ISM magnetic field, you should see such structure everywhere.
You mean on both sides, right?
No. I mean, imagine what you have, asymmetrical escape from a pulsar everywhere.
And it is,
and if you have such escape, it means you should have such escape everywhere.
Well, it's kind of what we see.
It means like it's no special conditions to escape to ISM from a pulsar nebula. It should be common feature, but it's rare.
Oh, well, it only happens when you have a pulsar moving at a highly supersonic velocity, so it immediately restricts you to only few pulsars, right? And then you have to have a pulsar that is actually sufficiently young, because if a pulsar overall produces very few particles, then you wouldn't be able to notice this even smaller fraction that is leaking out due to the limited sensitivity of the detector. So saying everywhere, it basically it means that not everywhere, because many systems, many pulsar Nibli will be excluded either based on not high enough proper motion or being too old. Yeah, for example, for crab, which is inside the supernova remnant, you wouldn't expect to see something like this, right?
I am talking about only about fast moving.
Yeah, but there's not too many. It's really like, okay, we can go to, these are like deep observations of some fast moving pulsars. The exposures vary, unfortunately. Yeah, so they're not all equally deep. So for Geminga, this structure is one-sided, kind of.
But this one, it's hydrodynamical jet. It's small size.
Yeah, but there may be, yeah, just band jets. Yeah. So
it's but like here we're talking about kinetic jets, which is much longer, which is impossible to be explained by hydrodynamical flow.
yeah, so but they're very too long, right? And so, but this is asymmetric still, right? Structure. Here we see hint on one side. Here it's one-sided. Here it is one-sided. Here it's also one-sided. You cannot see this contrast, sorry, but there's some evidence of the structure going this way. There's nothing here, maybe because this CCD somehow is, yeah, there's some maybe higher noise. I cannot comment right now. This is
there's a
XMM
question
image.
from Jules. Jules,
Yeah.
did you have your hand up?
Yeah. Go ahead, Jules. Sorry, I got engaged in this discussion too much. Yeah. Jules, did you have a question? I'm not sure if Jules can hear me.
Maybe no more.
But there's a question
maybe
from
you
Jane.
answered his question in the discussions with Maxime. But there's a question from Danielle.
Yeah.
Yes, hi. Thank you for the very nice talk. I was wondering if you could expand a little bit more on how you can use the measurement of the viewing angle of the nebulae to discriminate between the magnetospheric emission models.
Right. Sorry, I may have went through this too fast. So there are two angles, right, that the models usually predict. And I have some backup slides. Let me show you this. Let me just very quickly show you this. These are the typical plots, right, that magnetosphere modeling people make. And there's multiple groups that work on this and do this. And so these are plots that show these two angles, and then they predict either one peak or two peaks, depending on the values of these angles. They can predict peak separation, right, as a function of these angles. Yeah, so these are different models actually modeled by one group. It's outer gap and one pole caustic. And so even within one model, you sometimes have a range of options, right? Based on the measurement of a gamma ray light curve for some pulsar, you not necessarily have a single solution. Now, imagine that one of these angles, most likely this zeta, that's the viewing angle that you can actually infer from the morphology of the pulsar wind nebula. For example, let me show you like some easy example, like here, right? You can see that this termination shock shape is like almost a ring, right? But there's a little bit of a Doppler effect going on. So this edge is probably where the flow is approaching the observer, and this is where that is receding from the observer going away. And that is the Doppler shift. If you model both the shape, like how much it differs from a circle, and this Doppler boost, you can get the zeta angle. Zeta angle then restricts what kind of options you have in your modeling plots, right? Whether you can still have two peaks or not, what will be the separation. And maybe in one of the models, you will still have consistent solution, consistent both with gamma ray light curve and shape and the prediction from the pulsar wind nebula of this zeta angle. And maybe in the other model will not allow for consistent solution. Did I answer your question, Daniel? Did I?
Yes, but like this is only possible for like pulsar Y nebulae that are like aligned to us. Yes.
No, I mean, not, what do you mean aligned? Sometimes we see these very elliptical structures, right? This is no longer looking like a ring, right? It's mostly looking like ellipse, right? So these are larger zeta angle, maybe 65 degrees. So it's less aligned.
What I meant is that like the zeta angle is defined like the angle between the line of sight and the spin, but how is this zeta angle defined in the pulsar Y nebula? Is the same?
Sorry, which angle?
So, like the zeta angle in both the pulsar and the nebulae are defined in the same way? Or,
well, zeta angle is defined as the angle between pulsar spin axis and the line of sight, and alpha angle, That's the other one.
Yeah.
That is basically defining internal geometry of the magnetosphere. It's the angle between dipolar magnetic field axis and spin axis. That one is trickier to measure from the pulsar-Wien nebulae, but still, I think there's a connection, and it can be tested. Maybe if you can infer alpha from your magnetosphere emission model when you fix zeta based on the pulsar-Wien nebula, and then you see if indeed for a smaller alpha based on prediction of your magnetosphere model, you see stronger polar outflows and weaker equatorial component. And then this connects to an interesting, I think, test for the hydrodynamical simulation, which were done initially by Sergei Komissarov group, where these polar outflows are believed to be backflow from the equatorial outflow, which is confined by the hoop stress here. And Maxim can probably talk more about those kind of models than I can. Yeah.
Thank you, Oleg. We have
Thanks.
time for one last question, and it's in the chat, and it's
Oh.
about buried magnetars. You can't see the chat, so I can read it to you.
I
So-
can see.
Oh, yeah.
Yeah.
Take a look. It's
What
about
are buried magnetars? They were quickly mentioned, but have they been observed or modeled in supernova neutron star simulation, or are they at the moment purely speculative evolution branch? I regret Jules left. He could say much more, I think, about that. So the evidence for buried magnetars is maybe the best one is well, actually now there's multiple maybe, but one is from CCOs. So CCOs could be buried magnetars because the internal field can be still strong, but if you dump a lot of matter, that will take from fallback accretion after supernova explosion, it will take some time for that strong magnetic field to diffuse out, and that can be calculated. And all CCOs are very young, and so they haven't had this time. And so I don't think we see this. It will take some time for that to appear, and they will evolve potentially into maybe magnetars eventually. I don't know. These are maybe still speculative ideas, but the dipolar field in CCOs, as seen from observations from spin down, that's Jules and Eric Gottkill made those measurements, is low. That's why we say buried, right? That is low. And that's why they sometimes called anti-magnetars, these CCOs. But deep inside, they still can be magnetars.
Okay, so thank you, Oleg. That was really great, and
Thank you.
many good
Thank you.
questions. Thank you, everyone, for the discussion. And see you in 2 weeks. Thank you for coming.
Thank you. Bye-bye, everyone.
Bye.
Good to see you.
Thank you. Bye.
Bye.